If you have ever looked at a soap bubble, maybe you're taking a bath and there's some soap bubbles, or maybe you were blowing bubbles as a kid, or as a college freshman or whatever, and you look at these bubbles in a light, especially sunlight, you probably did see uh, swirls of rainbow colors. Now, we know that white light, like sunlight, is split into constituent colors by prisms and basically entering into new media and refracting differently. But a soap bubble's not a prism. And if you remember the thickness of the glass when we talked about dispersion of colors, the thickness of the glass actually had something to do with how those colors are spread out. But that can't be what's happening in a soap bubble. So, what in the world is happening? So, to find that out, let's introduce ourselves to what's called thin film interference. So, let's imagine that you have some sort of substance here. Right? It might be water, it might be glass, it could really be anything. But on top of that is a thin film of some other substance. This could be oil floating on water. It could be a thin soap bubble with air on either side. It could be an anti-reflective coating on a lens. Something, but it's the criterion we're looking at is it's thin in comparison with the material down here and the material up here. Let's give this a thickness T. I really don't like using T for anything but time, but this is, if you're in my class, this is what our textbook does, so I'm going to stick with it. So let's imagine that light comes in from the top. Now, the effect we're going to look at is much more pronounced when the light comes in perpendicular to the surface. But we're going to let that light bounce around and then come through and bounce around in here. And I can't really draw that if I bring in the light perpendicularly. So I'm going to let a light ray come in like this and just tell you that the effect we're looking at is going to be more pronounced and will work much better if the light ray is coming in straight. So just imagine that this is coming in straight. Okay, we know this. I'm saying ray, and that's what I've drawn, but we know that we're dealing with wave optics. We know that this light is a wave, and so what do we expect a wave to do at a boundary between media? So here's one medium, here's another medium, here's yet another medium. Two of these mediums might be the same, but at any rate, we have boundaries between these media. So at any boundary, we expect part of the wave to be reflected and part to be transmitted. Now, as I've drawn it, maybe you can convince yourself that I drew this refracted bent towards the normal. It could very well be bent away from the normal. I just picked one, doesn't really matter. But we've got this light being reflected. Now, let's follow the light that was transmitted. Whoop, I've gotten to another boundary. And notice I've gone a distance of about t, especially if I'm coming down straight. I definitely have gone t. If I'm coming in at a small angle, I've gone basically t. So I've traveled a distance t, but I hit another boundary. And at this boundary, part of the wave will be transmitted, but part will be reflected. I'm going to ignore the part that was transmitted, because that just keeps on going in this medium, and we never see it again. But I'm going to look at the part that is reflected. Okay, well, lo and behold, I'm at another boundary. And again, at this boundary, part of the light will be transmitted, part of it will be reflected. At this boundary, I'm going to ignore whatever is reflected back down into this medium and just look at the one that's transmitted. So now I have two waves that are arriving at some destination. There's an eyeball over here looking at this. So these waves are arriving at that destination after having taken different paths. So I've got the potential for a path length difference, right? This is what we've seen with all of these discussions about diffraction and interference, is if the path length is different, then I have the opportunity for both constructive and destructive interference. And this is actually how you see different colors in things like soap bubbles and oil slicks on the surface of roads. You have some wavelengths that experience destructive interference, some wavelengths that experience constructive interference due to this effect. Now, so if I take out certain wavelengths from white light, what I'm left with is, well, all the wavelengths that were left. Wavelengths are going to correspond to color. So if I see yellow on the surface of this oil or this soap bubble or whatever, what that means is the yellow has survived and some other colors have not. So I get a rainbow effect without a prism. There is still refraction, but the space here is tiny. T is very, very thin. And so I don't get the same sort of effect I do from a prism. The colors here are produced by addition and subtraction. That is constructive and destructive interference. Okay, so what is the path length difference here? Well, maybe you can see it. To a really good approximation, the path length difference is 2t, right? Go down, come back up. Now, that is an approximation, but it's a pretty good approximation, especially if I'm coming in straight down. Then my path length difference is exactly 2t. So I'm saying that this ray and this ray are arriving at their destination after having, one of which having been shifted 2t. Okay, well, we know some equations that relate path length difference to constructive and destructive interference. 2t is equal to m lambda. 2t is equal to m plus 1/2 lambda, where in both cases m is equal to 0. Make sure you can still see this. Plus or minus 1, plus or minus 2, etc., etc. So you can see that. Element of the set of integers. So in the multi-slit diffraction and double-slit diffraction, we've seen what we could do immediately. You say, oh, well, integer multiple of wavelengths. This has got to be constructive interference. Half integer multiple of wavelengths. This has got to be destructive interference. But there's something else we've got to take into consideration here. In fact, there are two other things that we need to take into consideration. The first one is the wavelength. As I go into this new medium, the speed of the wave changes. Remember my wave speed equation, v is equal to f lambda. Furthermore, remember that the conservation of energy prevents the frequency from changing. The frequency will stay the same, but the speed changes. What that means is that the wavelength has to change. Now let's think about it. If you have a wave outside of the medium that looks like this, and inside the medium it looks like this, right? The wavelength has changed, but you're trying to line up peaks and troughs of this wave after it gets back to this boundary with this wave. Then what you need to worry about is how this wavelength fits in the space allotted. Once it exits this medium, the wavelength will return to its original. But if what we care about, if there's a peak coming out from the reflected wave, to get constructive interference, we need a peak coming out from the retransmitted wave, and vice versa for destructive interference. So what I really have to worry about is not the wavelength out here. I've got to worry about the wavelength in here, the wavelength in the medium. For that reason, I'm going to subscript this with an n for the index of refraction of that medium. We didn't have to do that with double slit interference because we never changed media. We went through a slit, but if I'm in air on one side of the barrier, I'm in air on the other side of the barrier. But here I change media, so I've got to worry about the wavelength in the medium. Fortunately, I have a really good way to relate the wavelength in air, the wavelength in the medium, to the wavelength in air, lambda air, over the index of refraction of the medium. This, I can substitute this expression into either one of these equations because I probably know the wavelength in air. And this allows me to calculate the wavelength in the medium itself. So that's the first additional consideration we have to worry about. And that doesn't mess with these equations. It just means this term is a little different and I have to substitute, but no big deal. The bigger deal is what happens at the boundary. So let's talk a little bit about wave inversion, also called a phase shift, a 180-degree phase shift. If I have a wave, or let's say I have two waves propagating through some medium, and those waves look like this, we know what's going to happen. Here I'm going to get constructive interference. The peaks will add together, the troughs will add together, so I get constructive interference from this particular wave. But now, say someone, maybe a wizard, comes along and snaps his fingers. I don't have the editing software to actually make that work. And changes this wave into this wave just immediately. Well, I did have constructive interference, but when that wizard snapped his fingers, I've got now destructive interference because I've in effect shifted my wave by half of a wavelength. I've turned it upside down. Why are we talking about this? Where's there a wizard here? Well, the wizard lives in the boundaries. So as it turns out, if I look at the indices of refraction of these three media, where this is going to be N3, if I'm moving from a slow, if I'm moving into a slow medium from a fast medium, so I'm traveling in a fast medium, and then I move into a slow medium, what does that mean for my indices of refraction? If N1 is less than N2, remember the bigger the index of refraction, the smaller the speed. So if N1's bigger than N2, which is the same thing as saying if I'm moving from a faster medium into a slower medium, I get inversion. I phase shift. What does that mean? Well, if I have shifted one of my waves already by half an integer wavelength, then this no longer gives me constructive interference because the two waves are now already shifted regardless of the order. So if I get one phase shift or one inversion, the role of these equations flops. This one now becomes destructive interference. This one now becomes constructive interference because this shift will in effect put my wave back to what it used to be. It doesn't physically do that, but mathematically it gets me back to the condition of constructive interference. Fair enough. Well, the same thing is going to happen at this boundary, right? I'm not going to write this down, but if N2 is less than N3, that means it's faster here than it is here. Well, then I get another phase shift. So this one gets inverted back to that. So it's like I have no phase shift, right? If I have 0 phase shifts, this is constructive. If I have 2 phase shifts, one here, one here, this is constructive again because it's like I've shifted the wave an entire wavelength. And an entire wavelength means I get back to my constructive condition. So the upshot of this is if I look at the indices of refraction here and I find one phase shift or one inversion, I've got to make this constructive and this destructive. If I find 2 phase shifts or 0 phase shifts, that's possible. This is constructive and this is destructive. All right, let's do an example. That usually helps. So let's, don't go anywhere. Let's get my, it's going places. Let's get my media set up. So we'll say that this is water. I've got a large body of water. And on top of the water, I'm floating some oil. And above here, I have air. So up here, I've got N of air is equal to 1. Move it over so you can see it. In here, this is oil. Let's just let this oil have an index of refraction of about 1.5. And water has an index of refraction of about 1.33. Okay, so before we, let's go ahead and trace my light coming in. Just, you don't have to do this. Normally this would be done for you actually, but just to remind yourself what's happening. So I've got light incident from air onto oil, and then incident from oil onto water. Before I do anything else, let's count up my phase shifts and figure out which of these equations, sorry, this is T, which of these equations is going to get me constructive interference, which is going to get me destructive interference. I wrote that backwards, that's okay. Okay, so do I have, I'm going to write it this way, phase, not theta, phi, that's how we normally write phase shifts. Phase shifts, I'm just going to keep track of them here at the top and at the bottom. Do I have one at the top? Well, I'm coming from air into oil. Does the light slow down? Yes. Another way to ask it is the index of refraction here bigger than the index of refraction here? Yes. Then I get a phase shift at the top. Notice this is always going to happen when I'm incident from air onto anything because air has an index of refraction of 1. That's the fastest light's ever going to go. Of course, that's an approximation, but it's a really good approximation. The speed of light in vacuum and in air is about the same, so we just say that the index of refraction of air and of vacuum is 1. So light's going to slow down in the oil, so I get a phase shift at the top. Bigger index of refraction here than here. Okay, fair enough. Now, travel on down. I've got a larger index of refraction in the oil than I do in the water. That is to say, if this light ray were to pass into the water, which it doesn't, but if it were, it would speed up. So, do I get a phase shift at the bottom? No, I don't. So, I get one phase shift. That means I flip-flop the roles of these, and that means that this gets me destructive now, and this gets me constructive. Kind of strange, but because I'm phase shifting because of the reflection, it's a reflective phase shift, that's what it's called. This now gives me constructive interference. Okay, well, what I haven't given you, of course, is the wavelength of the light. Let's say that this wavelength in the air is red light, 432 nanometers. That's about the same wavelength as you find in a laser pointer, a red laser pointer, I should say. And so let's ask ourselves the question, what is the minimum thickness of this oil that gets me constructive interference in the red light regime? What is the minimum thickness? What is the smallest I can make T to give me a minimum thickness? There's one more little pitfall that's coming up that I want you to see, so that's why I'm asking it this way. So we've decided that this is my constructive interference. I'm going to write that down. 2T is equal to m plus 1/2 lambda n, but I'm going to write that as lambda a over n, right? That's the equation I saw over here to relate, or to tell me how my wavelength shifts when I go into a medium. So this n is going to be the n of the oil. It's in the medium, right? This is shifting in this medium, so when I plug in numbers, I'm going to plug in 1.5 for this. But the next thing to do, well, it seems like I'm done. I just need to solve for the thickness. But what is the minimum order here? Well, m is an element of the set of integers, 0, plus or minus 1. We're going to forget the negatives here. 0, 1, 2, 3, 4, 5, 6. Well, what's the minimum it could be? You might say 0, and I would say you're absolutely right. So let's pick out, because I've asked for the minimum thickness, m is equal to 0, which is going to give me 1/2. And so I get 2T is equal to lambda air over 2n. 0 here, 1/2 times that. So it looks like T is equal to lambda air, 432 nanometers, over 4 times n, which is 1.5. Let me actually run this number. Would have helped if I had a calculator available already. Here I am, being unprepared. That really should, sorry, that looks like 41.5. It should be 4 times 1.5. That's not going to work out. What I'm going to get here is 72. What are my units? Well, I left the 432 in nanometers, so I get 72 nanometers. It's usually pretty standard to leave this in nanometers. You deal with nanometers a lot when you have visible light. So I'm totally okay with thicknesses being given in nanometers. Okay, that seemed pretty straightforward, I think. Let me show you another one which has the little hidden pitfall that I was talking about. Now that we've seen the process, let's give the same setup. If I can make this stay. Same setup. I've got water, and I'm going to get a different kind of oil or some other substance that's going to float on top of the water. We like oil because we all know it floats on water. And I'm going to let this be air. So let's say that this n is equal to 1. Let's say that this is n is equal to 1.2. And this n of water is still 1.33. Let my light come in. We know what's going to happen. I'm going to ask the same question. What is the minimum thickness for which I get constructive interference for 432 nanometer light? Okay, well, same thing. Count out my phase shifts to figure out which of these equations gets me constructive, which gets me destructive. I need to subscript that with an N, right? Okay, same idea. Do I get a phase shift at the top? Well, I'm moving from air into anything, so yes, I do. Now look at the bottom. Do I get another phase shift here? Well, 1.2 is less than 1.33. You know, the way to think about that is the light would slow down moving into the water from this medium. And so yes, I get one at the bottom. So 2 phase shifts means I go back to my original constructive equation. Can grasp that word for a second. My original constructive equation is this one. So 2 phase shifts, 0 phase shifts, 4 phase shifts, if you have that, means this is constructive. 1 phase shifts, 3 phase shifts, 5 phase shifts means this one is constructive. But in this case, I've got 2. This is constructive. So I'm going to do this same thing. 2t is equal to m times lambda a over n, substituting in for lambda n. And now let's do the same thing we did before. What is my minimum order here? If I'm looking for the minimum thickness, I'm trying to make t as small as I can. I need to make this as small as I can. So a while ago I picked out 0 and it worked just fine. Well, what would happen if I use 0 here? Well, it certainly would minimize it. But the right side of this equation would be 0, which means the left side of this equation would be 0, which means the thickness would be 0. If the thickness is 0, there's actually nothing here. Right? That doesn't actually make physical sense. Mathematically, it makes perfect sense. But physically, I'm going to have to restrict my m value here. I can't use 0 because that tells me there's nothing here. That means the thickness is 0. So the smallest m I can get away with here is 1. So let's let m be 1. And what I get if I solve this is t is equal to lambda in air over 2n. That's equal to 432 nanometers over 2 times 1.2. And if I do that, I get 180 nanometers. So that would be the minimum thickness that would give me constructive interference for 432 nanometer light in this system. If you want to find the minimum thickness for destructive interference, it's going to proceed the same way, right? You count up your phase shifts, you figure out which one's destructive, and you go with that one. You got to be careful with this one, though. M can be 0 here. I should say you got to be careful with this one. M can be 0 in this equation. A little difficult to justify physically M being 0 in this equation.